All right, everyone. Welcome to our topic. I'm very excited to be here in the FOSSASIA Summit, sharing our topic, Introduction to openEuler Embedded and its Innovative Features. My name is Yongmao. Now, I am the committer of the openEuler MCS repository, responsible for developing the MICA framework and auditing codes for developers when they upload their codes to our repository. Okay, in the following half an hour, I would like to introduce two main topics. The first one is Introduction to openEuler Embedded, including its key features, its general architectures, and its application scenarios. Then I would like to introduce the mixed criticality system framework and its management framework for supporting multi-OS running on a single embedded OS platform. Okay, so firstly, thanks to Dr. Sheng's presentation about openEuler, now we may have a better understanding of what openEuler is. As we know, openEuler covers four main scenarios, that is server, cloud, edge, and embedded. And openEuler Embedded focuses on providing competitive operating system technology for resource-limited hardware platform. And because of the need to build customized OS, we choose Yocto as our composing system. So it's an open source project from Linux Foundation, and it's provide an easy way to tailor our operating system. Okay, so after knowing the relationship between openEuler Embedded and openEuler, now I would like to provide a definition of what it really is. So we define it as an open and comprehensive embedded software platform. So it's not just the embedded Linux, but it's like a solar system. The sum is the embedded Linux. It provides the unified build, rich features, ecosystems, and standardized interface. And we also have some non-Linux planets which provide rich features, like T can provide security, RTOS can provide hard real-time, and bare metal can provide extreme performance, while the embedded virtualization can provide isolation and resource management. Okay, so let's take a deeper look to openEuler Embedded. So the blue part are the scope of openEuler Embedded. So for the hardware, we can support more diversified hardware than the cloud and server scenario. And for the application, we mainly support operational technology applications. And we would like to attract users and vendors to build your own application based on openEuler Embedded to provide more interesting features. And at the bottom part, we have the Fusion Dock, which is a collection of technologies to support multi-OS running, so including virtualizations, containers, etc. And above that, we have the MICA framework, which is the management framework for lifecycle management for multi-OS. And we can also provide a communication framework for different OS communication. And above the MICA framework, we have various types of OS. For Linux kernel, we have configuration and optimization for different scenarios. And above Linux, we have many different kinds of interesting features. And the RTOS, we don't have a best for all option for it. So we supported different kinds of RTOS. So firstly, the Uniproton, which is a very interesting RTOS, also from openEuler community. And we have Zephyr, which is a well-known operating system worldwide, and RTOS Red, and very popular RTOS in China. And also, reliability is our focus. So we would like to provide the performance tuning, debugging, and tracing methods. For example, the MICA framework provide debugging methods for RTOS who has realized the GDB stop. And also, the tools and infrastructure are also very important because they are the backbone of our system and they are supporting our daily work. Okay, so let's let's move down a little bit to see the key features of our system. We have 1 plus x plus 1 feature. The first two features are the invariants, which is the two legs to support our operating system. That is the embedded Linux and the infrastructure, with the X features in the middle. And for the embedded Linux, we have high quality maintained kernel, which is the same kernel as other kinds of distributions of openEuler. And above that, we will do specific optimizations and configurations, like we will apply prim-RT patch for soft real-time applications, and we will do fine-grained configurations and tuning to reduce binary size and memory consumption. As for the infrastructure, we choose Compass AI as the foundation technologies for our CI/CD system, and we choose Yocto as our building framework, as I said before. And we store all of our codes in Git, which is something like GitHub, but a more popular one in China. In the middle, we have the DSoft bus, which is a kind of a collection of technologies to manage and connect different node devices in a local network. And we have our mixed criticality system. So it provides the foundation technologies like hypervisors and containers, and we provide a management framework above it. And we also support embedded robot runtime, like we integrate ROS2 into our system. And we also have the embedded, we also want to provide more support for embedded edge and embedded AI in the future. So like we will integrate Cube Edge K3S into our system so that in the future, we will improve the collaboration between the cloud, edge, and embedded. And also, we will integrate mainstream AI framework in the future, like the TensorFlow, PyTorch, or Mindsboard. Okay, so after knowing the key features, now you may be wondering, like, so what does it look like when the openEuler embedded is running? So actually, we have 4 running modes. The first one is the very typical mode. So that is, we only run one Linux based on the embedded system. So now we can, get the advantage of Linux ecosystems, but the cons are very obvious. There's no guarantee of hardware real-time or high reliability, which are the advantage of RTOS. As a result, in the following 3 modes, we can run more than one OS based on a single embedded platform. For the AMP mode or the asymmetric multiprocessing mode, we deploy openEuler embedded and RTOS based on different types of CPUs. Like for example, we deploy openEuler embedded on A-tier ARM core cluster, and we deploy RTOS on M-tier ARM core. And the hardware resource is static allocated. So the disadvantage is the number of OS is limited by the hardware resources. Like if we only have 4 CPUs in the embedded system, then we cannot run 5 OS based on it. To resolve this problem, we introduce the virtualization mode, which can, which use the virtualization technology to provide, in theory, unlimited operating system to, provide the chance to run unlimited operating system based on a resource-limited hardware platform. However, because we have poor support for heterogeneous cores, so hypervisor can only run on homogeneous cores cluster. As a result, in the end, we have diffusion mode. So we will run AMP mode for heterogeneous cores, and we will run virtualization mode for homogeneous cores. All right. So actually, we can deploy our operating system as 3 different kinds of system. So firstly, we can deploy it as a server so that it can control different kinds of node devices through internet. And we can also deploy it as an edge-based system for edge computing. And we can also deploy it as just, as it originally designed for the embedded system. And it can control different kinds of peripherals. Okay, so I want to make a small summary for our ecosystem. openEuler Embedded is an open and comprehensive software platform. It includes the embedded Linux part, which gains the kernel from openEuler community, the same kernel as the other kind of distribution. And we use Yocto as our building system, which is different from other distribution. And we also have some non-Linux part, like RTOS and hypervisor. For the applications, we support industrial IoT, robotics applications, energy industries, and BMC, which stands for Baseboard Management Controller. And we have some applications for it, like we have applied our operating system into the industry controller, the unmanned vehicles, and some interesting robots. Like last year in the openEuler Summit, there is a very interesting robot. If you stand in front of the camera, the painting robot can paint a picture for you. So it's also run the openEuler embedded inside it. All right, so I would like to introduce the development board. So EulerPi is a series of development boards designed for running openEuler embedded. And HiEulerPi is one of it. And its SoC is SD3403, designed by HiSilicon, so we name it HiEulerPi. It has very powerful hardware and can run complex software based on it. And its usage is mainly for industrial control and robotic applications. It can support various types of communication protocols and peripherals. Okay, so secondly, I would like to introduce our mixed criticality system framework. So at first, I would like to make a small metaphor to help you understand what is mixed criticality system. So in the past, like we only have small flower pots. In each flower pot, we can only plant one single type of flower with very limited quantity. But with the time flies, we have more mature pot making technologies. And nowadays, we have very big flower pots. In each flower pot, we can plant various types of flowers. And also, each type of flower are isolated. For example, if one bunch of flower dies, it will not affect other bunch of flowers. Okay, let's move back to the field of computer science. In the past, we only have very simple hardwares, like the tiny MCU. So we can only run something like bare metal applications or small RTOS based on it. And nowadays, we have very complicated SoCs with multi-cores, even heterogeneous cores, so that we can run more than one OS based on the SoC. So like we can run Linux plus RTOS plus other kind of bare metal applications. But to ensure the safety, we need to provide an isolation mechanism so that if one OS dies, it will not affect other OS running. Okay, so maybe now you have a general understanding of what MCS is. So now I would like to provide a more clear, more strict definition. So as its name says, MCS stands for Mixed Criticality System. So literally, it just stands for a system with mixed criticality components. So what does criticality stand for? It mainly refers to safety, but it can also extend to other notions like real-time, security powers, etc. And we mainly focus on 3 parts of MCS, that is the deployment, quarantine, and scheduling. So firstly, we need to deploy different kinds of OS onto the platform so that we now have the mixed criticality. But that is not enough because to ensure safety, we need to provide quarantine between different OS. And then to achieve a better overall performance, we need to implement scheduling so that, like the virtualization, if one OS is in idle state, it can, allocate resource for other kinds of OS to achieve a better overall performance. And we believe it's the future trend of embedded systems because of two reasons. From the server side, the hardware is evolving from distributed one to centralized one. Like for example, the ECU in automotive vehicles, they can only do very simple tasks. But nowadays, they are evolving into a zone controller to control a large area of hardwares. So we need a more complex software to do the control. And from the client side, we are having more and more complex node devices, like the drones nowadays. They should keep balance at the same time while taking photos and transmit the data back to the cloud. They are doing many complex things in the same time. So we may need, more than one OS for the different applications. All right. So I would like to introduce our mixed criticality deployment framework. Why we call it deployment framework is because for the quarantine and scheduling mechanism, they are implemented by the foundation technologies like virtualizations and containers, which is included in the Fusion dock part. And our MICA framework mainly focuses on 4 parts. That is the lifecycle management, cross-OS communication, service framework, and multi-OS build infrastructure. So for the lifecycle management, we provide a unified interface for multi-OS management so that we can hide the differences of the foundation technologies in Fusion dock. As for the cross-OS communication, we provide a shared memory-based and lockless framework to support efficient communication. As for the service framework, we define the service interface as different OS provide different services. And in the end, we also provide a unified resource description so that different OS can dock into our MICA framework more easily in a more standard way. Okay, so we can take a deeper look into our framework. So for the lifecycle management framework, actually because it needs to control the hardware. So actually it's an platform independent framework. We will take RMVA architecture as an example. So firstly, if the MICA framework wants to boot up the remote processor, it will send an SMC call to the bottom level firmware, and the bottom level firmware will do the actual work to boot up the CPU of the remote operating system. And for our framework, we mainly use the remote proc framework as our base technology for doing most part of the lifecycle management. So remote proc framework is a framework in Linux kernel, and it provides a standard way to abstract the remote operating systems. Like in the framework, the remote operating system, each the remote operating system is a remote proc instance. So in our MICA framework, we have many remote proc instances. And below the remote proc instance, we have a unified resource manager to manage all kinds of resources in our MICA framework. And above each remote proc instance, we will call the interfaces of remote proc to load our OS binary to the destination memory and parse the resource table and boot up, etc. Doing a lot of things. And for the resource table, so it's a very, very interesting and very special data structure in ERF format. Each entry of the resource table indicates a type of resource for, between the two OS, as there is a shared resource. Okay, as for our service framework, for now, we mainly depend on the RP message framework from kernel as well. And if we have one service between the two OS, then it will establish one specific endpoint for it. But for the abstraction, the service is another kind of abstraction other than the endpoint. So it's a more abstract notion. For example, we can have pseudo terminal service, that is the PTY service. But for the two OS, they may have more than one PTY connection. As a result, for a single service, we may have more than one endpoint, mapped to it. And also, we can provide self-defined service like the debugging for RTOS with GDB stub. And the bottom level is not implemented with RP message framework. We are implemented with our own defined data structure. All right. So then I would like to introduce the history and the future of the MICA framework. So in the past, we only implement the OpenAMP-based MICA framework so that we can only support many deployment, but poor quarantine and scheduling. And now we are developing with many, excellent virtualization technologies like the VMs, like Rust ciphers, and we also want to use the lightweight containers to, to enrich our ecosystem. And as a result, in the future, we want to support both heterogeneous and both heterogeneous and homogeneous cores. And support even, the collaboration between the node device and the cloud systems. Okay, so I would like to show our envision of the future framework. So firstly, we will deploy many OS based on the, the homogeneous core cluster with a type 1 hypervisor. Because it's the type 1 hypervisor, even though different virtual machines are isolated, they actually have a management VM for management the whole hypervisor system. Sorry, the virtualization system. And because the management VM is responsible for take control of the communication in and out the system. So like if the two VMs want to send interrupts to each other, they need to pass through the management VM. But to improve the efficiency of data transmitting, the two VM can directly establishing their data transmission channel. And secondly, we can also deploy our operating system to heterogeneous cores. And the communication can happen in the physical memory. Of the physical layer, we have the VirtIO protocol as the link layer protocol. And above that, except for RP message protocol, which is a kind of transport layer protocol, we also want to support other protocols like UDP and TCP. And above that, we also want to establish our own RPC framework, that is the remote procedure call framework. And thirdly, we also want to modify the ISULA so that ISULA is a kind of lightweight container technology, which is something like Docker, but it's from the openEuler community. And we want to modify ISULA so that users can deploy operating system through K3S, through ISULA to the MICA framework, to here or here, to the embedded device. All right. So at last, welcome to engage in our openEuler community, and these are the resources for you. Okay, thank you for listening.